Did the universe have a beginning, or has it always existed? Join us as we explore one of the deepest mysteries in cosmology. The question of cosmic origins challenges our understanding of time, space, and existence. Let's start with the traditional Big Bang model and what it tells us about the beginning. According to the standard Big Bang model, the universe began approximately 13.8 billion years ago from an incredibly hot and dense state. At time equals 0, the temperature was approximately 10 to the 32 Kelvin, an unimaginably hot state. The universe expanded rapidly from this initial singularity, cooling as it grew, creating the cosmos we observe today. But here's the fundamental problem. What actually happened at time equals 0? Our equations break down at this point. At the initial singularity, our laws of physics completely break down, creating what we call a mathematical singularity. The singularity problem is one of the biggest challenges in cosmology. A singularity represents a point of infinite density and infinite spacetime curvature, where our mathematical descriptions fail. As density approaches infinity, and the scale factor approaches 0, we lose predictive power. This graph shows how density spikes to infinity as we approach the singularity, indicating our theories are incomplete. This raises a profound question. Did time itself begin at the Big Bang, or was there something before? To understand what might have happened, we need quantum gravity at the Planck scale. The Planck length, about 1.6 times 10 to the negative 35 meters, is where quantum effects dominate gravity. Similarly, the Planck time is approximately 5.4 times 10 to the negative 44 seconds, the earliest moment we can meaningfully discuss. Below the Planck scale, spacetime becomes a quantum foam, with violent fluctuations, where classical concepts break down. This quantum foam represents the chaotic nature of spacetime at the smallest scales, where our intuitions about time and space fail. Now let's explore cyclic models that challenge the idea of a single beginning. What if the universe goes through endless cycles of expansion and contraction, with no true beginning or end? In cyclic models, the universe oscillates between expansion and contraction phases, bouncing eternally without a beginning. Each Big Bang is followed by expansion, then contraction, into a big crunch, which becomes the next Big Bang. The ekpyrotic model proposes that our universe exists on a membrane or brane, and collisions between branes create these cycles. When these higher dimensional branes collide, they release energy that appears as a Big Bang in our three-dimensional space. A major problem: if entropy increases with each cycle, how can the universe return to a low entropy state for a new beginning? Quantum cosmology offers another radical perspective on the beginning. Stephen Hawking proposed the no-boundary condition, suggesting the universe has no boundary in imaginary time. The wave function of the universe is calculated by integrating over all possible geometries with the action s. In imaginary time, the Big Bang becomes smooth, like the North Pole of Earth. There's no edge or singularity to worry about. Just as there's no edge when you reach the North Pole, there's no singular beginning in this model. The universe simply is. In this framework, time itself emerges from a timeless quantum state, making the question of what came before meaningless. Loop quantum cosmology offers yet another resolution to the singularity problem. In loop quantum gravity, spacetime itself is quantized at the Planck scale, made of discrete building blocks. The Big Bang singularity is replaced by a big bounce, where the universe contracts, then bounces back. The universe smoothly bounces at a minimum size, avoiding the singularity and suggesting a previous contracting phase. The maximum density reached is about 0.41 times the Planck density, enormous but finite, preventing infinite densities. A previous contracting universe reaches this maximum density and bounces, becoming our current expanding universe. Eternal inflation presents a different challenge to the concept of a single beginning. Inflation theory proposes that the early universe underwent rapid exponential expansion, solving several cosmological puzzles. The scale factor grows exponentially with time, with a Hubble parameter of about 10 to the 35 inverse seconds. But inflation might never end everywhere at once, instead creating an infinite number of pocket universes continuously. Each bubble represents a pocket universe where inflation has ended, but the background continues inflating eternally. This suggests there's no global beginning to the multiverse, only local beginnings for individual pocket universes like ours. The holographic principle offers a radically different perspective on spacetime and beginnings. The holographic principle states that all information contained in a volume can be encoded on its boundary surface. The entropy is bounded by the area in Planck units, not the volume, suggesting reality is fundamentally two-dimensional. Our three-dimensional universe might be a holographic projection from information stored on a two-dimensional surface. This raises a fascinating question. Was the Big Bang itself a holographic projection from a boundary condition? If so, time itself might be an emergent phenomenon from more fundamental timeless physics at the boundary. Roger Penrose proposed conformal cyclic cosmology, another radical model. In Penrose's model, the infinite future of one cosmic eon becomes the Big Bang of the next eon through conformal rescaling. The metric of the next eon is related to the previous one through a conformal factor omega squared. The universe cycles through infinite eons, each beginning with a bang and ending in infinite expansion and heat death. At the end of an eon, only massless particles remain, and for them there's no sense of time or scale. This timeless, scaleless state naturally matches the conditions of the next Big Bang through conformal symmetry. Let's tackle the fundamental question: what existed before the Big Bang? Option 1. Time itself began at the Big Bang, so asking what came before is like asking what's north of the North Pole. Option 2. Something existed before, but all information from that era was erased during the Big Bang transition. Option 3. Cyclic or eternal models, where there simply is no absolute beginning to explain. These three possibilities represent fundamentally different views of cosmic history and the nature of time. Currently, we lack the experimental evidence needed to distinguish between these competing models of cosmic origins. What can observations tell us about these different models? The cosmic microwave background gives us a snapshot from 380,000 years after the Big Bang, but not earlier. Today's CMB temperature is 2.725 Kelvin, cooled from billions of degrees by cosmic expansion. Primordial gravitational waves might let us probe earlier times, potentially even revealing signatures from before the Big Bang. These ripples in space-time could carry information from the earliest moments, or even from a previous cosmic cycle. Data from the Planck satellite supports simple inflation models, but hasn't detected bounce signatures or cyclic patterns yet. These scientific models have profound philosophical implications. Is our insistence on a beginning just a limitation of human thought or a genuine feature of reality? Perhaps the universe exists in a way that's ontologically prior to time, making temporal questions inapplicable. Time might emerge from a more fundamental, timeless reality, like temperature emerges from molecular motion. Quantum mechanics already suggests reality doesn't have a definite past until measured. Extending this to cosmology is radical. Entropy presents a crucial challenge to cyclic models. The current entropy of the observable universe is approximately 10 to the 103 Boltzmann constants. But at the Big Bang, entropy was much lower, around 10 to the 88, creating the entropy problem. How can a cyclic model reset the universe to such a low entropy state at each bounce? This remains a major puzzle. The second law of thermodynamics says entropy always increases, but cyclic models need it to decrease somehow. Some models propose information loss or new physics at the bounce point that could reset entropy, but this remains speculative. Some theories propose the universe tunneled into existence from literally nothing. Quantum mechanics allows particles to tunnel through energy barriers they classically couldn't overcome. The probability of quantum tunneling is proportional to e to the negative Euclidean action over h bar. Perhaps the universe tunneled from a state of nothing to something, creating itself through quantum fluctuation. Through quantum tunneling, the universe could emerge from a state with no space, no time, no energy, creating all of reality. But what does nothing really mean? Even a quantum vacuum has structure and laws, so is it truly nothing? String theory offers its own perspectives on cosmic origins. In string theory, fundamental strings vibrate in 10 or 11-dimensional spacetime, with extra dimensions we don't observe. The characteristic string temperature is around 10 to the 32 Kelvin, roughly the Planck temperature. Some string scenarios propose our universe emerged from a lower dimensional brane, or through brane collisions. These vibrating strings in higher dimensions could provide a more fundamental description of spacetime and its origin. In string gas cosmology, the early universe was filled with the hot gas of strings that evolved into our current state. The anthropic principle offers a different approach to these questions. The anthropic principle states we observe this particular universe because we can only exist in universes with suitable properties. If eternal inflation is correct, there are infinitely many universes with different physical constants and laws. Among countless universes, we necessarily find ourselves in one capable of supporting life and observers like us. The question of the universe's beginning might be partially answered by this selection effect across the multiverse. What is the current scientific consensus on these deep questions? Scientists agree the standard Big Bang model works extremely well for times after the Planck epoch. But before the Planck time, physics becomes uncertain, and multiple models remain viable candidates. For times less than the Planck time, we simply have an open question with no consensus answer. Known physics breaks down into multiple speculative frameworks, each offering different answers about cosmic origins. We need a complete theory of quantum gravity to make definitive statements about the universe's beginning or lack thereof. What future observations might help resolve these mysteries? Future gravitational wave detectors like LISA and the Einstein telescope might detect primordial waves from the earliest moments. Advanced CMB polarization experiments could reveal signatures of different early universe scenarios. With precision cosmology, we might find subtle signatures of bounces or cycles imprinted in the cosmic structure. These next-generation instruments will probe deeper into cosmic history than ever before possible. Remarkably, definitive answers to these ancient questions might come within the next 20 to 30 years of observations. The mathematics involved in these theories presents enormous challenges. Solving the equations for quantum gravity, loop quantum cosmology, and string theory requires advanced mathematical techniques. Understanding the behavior of black holes and the early universe pushes the limits of current mathematical understanding. Mathematicians and physicists are working together to develop new mathematical tools to tackle these challenges. Developing new mathematical tools is crucial for making progress in understanding the universe's origins. In conclusion, the universe's beginning remains one of the greatest mysteries of our time. Multiple theories, including the Big Bang, cyclic models, and eternal inflation, attempt to explain the universe's origins. Each theory has its strengths and weaknesses, and the debate continues among scientists and philosophers. The search for a complete and consistent theory of the universe's origins continues to be an active area of research. Future observations and experiments will help to determine the most accurate theory of the universe's origins. The mystery of the universe's beginning may be solved in the next few decades, revolutionizing our understanding of the cosmos.